everyone. In this video, we're going to look at something called the definite integral and its connection to area. So we're going to start by considering a function y equals f of x. Now I've drawn it here as sort of a polynomial function. It doesn't have to be. And we're going to start where the area between that function and the x-axis is continuous on a particular interval. So from a to b here. And it's not broken up. It doesn't cross the x-axis. It's all just one region. We will look at what happens when it isn't continuous, but for right now, let's stick with continuous. And we're going to define a function as the area function. So a of x, representing the area that I've got shaded in yellow here, the area under y equals f of x, between a and some value x that is in the interval from a to b. So I'm also now going to extend that out and say, okay, well, what if I go to x plus h? So this larger area would be a of x plus h. And based on what we know from derivatives, you can probably predict that we're going to look at what happens as h gets closer and closer to 0. But to start, let's consider this sliver of area between the two. This little bit here between a of x plus h and a of x. So in other words, if I take the difference between those two, which again, if you think about derivatives, the difference between some function at x plus h and some function of x was part of the limit definition of a derivative. But that area here is close to a trapezoid. So this approaches a trapezoid as h goes to 0. And the area of that trapezoid, well, the area of the trapezoid is the average of the areas of the bases. Now, in this case, the bases are the vertical lines. So right here and right here. So the heights of those are going to be f at x and f at x plus h. Those are the heights of the vertical lines. So the average of the bases times the height, or in this case, width of the trapezoid, which is the horizontal distance. So that's the area of the trapezoid. So we're going to set that aside for now, and we're actually going to look at what happens if we try to derive a of x. So the derivative of a of x by the limit definition is the limit as h approaches 0 of a of x plus h minus a of x over h. But the numerator here is the trapezoid. And as h is approaching 0, that area, the area with the curved top, is getting closer and closer and closer to the area of the trapezoid, which has a straight line top. So I can replace that expression with my area for the trapezoid. So this is the limit as h approaches 0 of f of x plus h divided by 2 times h all over h. So now my h's cancel, and I have no more problem of 0 over 0, so I can simply substitute, okay, what happens when h equals 0? When h equals 0, this is now f of x plus f of x over 2, which is 2f of x over 2 is just f of x. So what that means is that a prime of x, so the derivative of that area function, is my original function. Or more specifically, because I don't actually know the area function here, the area function is an antiderivative of the original function. So an antiderivative of f of x. So this is what's called the fundamental theorem of calculus. And it sets up the relationship between the antiderivative of a function being related to the area under that function. But let's summarize a little bit here. So we had two different types of integral. We looked at the indefinite integral, which is what defines a function. So the indefinite integral is basically an antiderivative. It finds a new function, more specifically a new family of functions, because we'll have plus c, which we can't always find if we don't have an initial condition. But the point is our solutions are functions, whereas definite integrals are numerical. So if I look at this definite integral where I put upper and lower bounds here, these values of a and b are real numbers. And this then gives me a definite integral which corresponds to a numerical value of the area under that curve, so between the curve and the x-axis, for a particular interval from A to B. Now, we'll get into the details of, well, what happens if that area isn't continuous, or what happens if the function is below the curve, and so the area is underneath the x-axis instead of above the x-axis. We'll get into all those details a little later. But first, let's make the connection that how we calculate the definite integral. So how we calculate the definite integral is to find an antiderivative. Now, it doesn't matter which one. And I will actually, in the first example that we do, illustrate why it doesn't matter what the constant is. But we pick any antiderivative of f of x. We evaluate that antiderivative at b, and we evaluate that antiderivative at a, and we find the difference between the two. So let's look at an example so that we can sort of illustrate why it doesn't matter which antiderivative we choose. So we want to find the area enclosed by y equals 2x squared, y equals 0, which is the x-axis, and x equals 1 and x equals 2. So that'll be this area here. We want to find the area of that region. Now, again, it's kind of close to a trapezoid, but for a trapezoid, there would be a straight line between the points 1, 2, and 2, 8. So if you wanted to just approximate this area, it wouldn't be terrible to divide it and figure out the area of the trapezoid if this were just a straight line. But we can use an antiderivative. So this is a definite integral situation. It's the integral from x equals 1 to 2, so always at the x values because we're anti-deriving with respect to x, of the function 2x squared, again, dx, so that I know this is with respect to x. That definite integral equals the area. Now, I just need any antiderivative, but I'm going to use the general one here. So I'm going to say an antiderivative of 2x squared is 2x cubed over 3 plus c. So I don't know what c is. I have no way of knowing what c is. And I want that between 1 and 2. So in order to calculate this, I evaluated at 2, so 2 times 2 cubed over 3 plus c, minus 2 times 1 cubed over 3 plus c. Now, the reason the constant doesn't matter is because of the subtraction, it's always going to cancel. So because it will always cancel, we don't usually bother writing it. We just assume that, well, let's let c equal 0, because this would work with literally any of the antiderivatives. Does not matter which antiderivative we choose, might as well choose the easiest one where c equals 0. So now that I've figured out I don't need the constant, this is 16 thirds minus 2 thirds. So in other words, the area here is 14 thirds units squared.